Okay, Tube, in this video we're going to discuss the concept of an nth root and also talk about some notation we use to represent those roots. Okay, and so in terms of roots, what we mean by them, let's go ahead and start with a familiar concept. That would be like a square root. And we often write this radical symbol here, and so this is referred to as a radical symbol. And basically, when we ask for the square root of a number, so for instance, the square root of 9, what we're really asking for is, can we think of a number that when we take it times itself, we get 9? So I would say that the square root of this is 3, but the only reason why the square root of this is 3 is because that's the number I can take to the second power in order to get this thing right here. So in terms of square root, maybe instead of asking for a square root, I ask for things like a cube root, and I start asking questions like, hey, what could I take times itself 3 times to get 27? And then I can work backwards answering questions like that with 3, of course, and saying that I could use a cube root in order to do that. So when we talk about a root, we're really asking, can you think of a number that when we take it times itself, say this many times, we get this value over here? And so extending this, we say, for example, 2 is a cube root of 8 because 2 to the third equals 8. In general, we're looking for, with integers n greater than 1, if b to the n equals a, then b is the nth root of a. We're looking for this b number right here. And so whatever n is, this integer greater than 1, we could say that b is a root of a because we could take b times itself n times to get that a in the first place. And so we refer to this as the nth root of a, and we say an nth root of a is written just like this right here, and I'll rewrite it again. So basically, if a square root is written this way, we say the nth root is written this way right here. And so there are a few bits of vocabulary I want to put in here. We call this the index of the radical. And the index of the radical out here basically tells you what root you are taking. So for instance, over here on the square root of 9, we could write the square root of 9 this way, or we could write the square root of 9 this way. We just assume that when you don't write an index, you mean the square root. But any other root, we have to write a little index out here. We refer to this right here, this inner portion, as the radicand. Okay, and then this would just be our radical symbol right here. And so looking at this here, we say that the nth root of a is written as the nth root of a, where n is the index of the radical here. And so a couple of things I want to say about this. The interesting thing is, if we were to raise a to the 1/2 power, the 1/3 power, the 1/4 power, what we see here is this a to the 1/2 power. If we square it, then we get a to the, now one of our properties of exponents that says when you raise a power to a power, something like x squared to the third, you could see that this would be x squared times x squared times x squared, which would really be x times x times x times x times x times x. We would get 6 total x's. And so the rule here is you multiply your exponents. But basically, when you multiply a half times 2, we get a to the 1. So in other words, a to the 1/2, that is the number I could take times itself twice to get a. So in other words, a to the 1/2 is the square root of a. And we say that a to the 1/3, if I cube that, then I get a to the 1/3 times 3, which is really just 1. In other words, I get a. So basically what we're saying is a to the 1/3 must be the cube root of a because it's the number that when I take it times itself 3 times, I get just a. And then likewise, we say that a to the 1/4 must be the 4th root of a because when I take it to the 4th, I get a to the 1st, or I get a. So we say because a to the 1/2 is a number whose square is a, we could also write the square root of a as a to the 1/2. And so in general, we could say this right here. We'd say the square root of a is equal to a to the 1/2. Then we'd have the cube root of a would be a to the 1/3. And likewise, we could extend this to the 4th root of a. If I took a to the, the 4th root of a, we could say this is a to the 1/4 power. But in general, for an nth root of a, we say a is being taken to the 1/n. And these two things mean the same thing, where n is the index or the root that we are taking. So let's take a look at this definition down here. We say real nth roots of a, letting n be an integer greater than 1. So our index is just some root greater than the first root. And let a be a real number. So we're going to split this up here, but we say if n is an even integer. In other words, if you're taking the square root of a number, if a is negative, then no real nth roots exist. And so what we're going to say is this. The nth root of a, where a is negative, this would be imaginary, is basically what we want to write. We can't take the square root of a negative, or the 4th root, or the 6th root, or the 8th root, or any even root of a negative. You get imaginary results. Now, what if we're taking the nth root of 0? Well, when we just get 0, we get one real root, and it's just 0. But if we take the nth root, where n is even of a positive thing, then what we get is that plus or minus that we see out front. So plus or minus the nth root of a, or another way to write this is plus or minus a to the 1/n, where that is the nth root of a. So now when we say n is an odd integer, I'll skip to this one right off the bat, but if a equals 0, then the nth root of 0 is still 0, okay? But in terms of if a is negative, or a is positive, in this case we don't get any imaginaries. We can actually take the odd root of a negative thing. And so in each case we get a to the 1 over n, or just the nth root of a, one real root. So what we're going to do is we're going to evaluate these over here, find the indicated real nth roots of a. And so let's go ahead and take a look at this right here. The first thing I'm going to suggest is that we actually write out what we have. So our a here is 16, and what we're doing is we're taking the 4th root of this. And another way I'm going to write this is 16 to the 1/4 power. But really the question we're trying to answer is this. Hey, what number could we take times itself 4 times and get 16? And I can think of 1, I can think of 2. And because this is an even root, we have to write a plus or minus, because it could have been a negative 2 to the 4th power that gives us 16, or it could have been a positive 2 to the 4th power that gave it to us. So now looking down to this one, let's write our root here. We have negative 125 in our radicand, and we're taking the cube root, or the 3rd root. So I'm also going to write this as negative 125 all in parentheses to the 1/3. We say, what number could we take times itself 3 times and get a negative? Well, first of all, it must be a negative, and only a negative that taken times itself 3 times gives you a negative result. And also I could think of 5. 5 times 5 is 25, times another 5 is 125. So we see our cube root here is just negative 5, whereas up here it was both the positive and the negative 2. Let's take this. We have the square root of negative 49 here. And because this is a 2 right here, I'm actually not going to write it. And what I'm going to write is a non-real answer. As a matter of fact, what we get is plus or minus 7i. But basically what we find out is you don't get a real root here, because we're taking an even root of a negative value. And then this last root here, we have a 5th root of 243, which is also 243 to the 1/5 power. So one thing I want to say about this is I'm not really sure what this is. So I'm going to do a little guess and check. And if I said 3 to the power of 5, that was just guessing, but I'd say 3. It comes out to be 3. So now should it be a positive 3 or a plus or minus 3? And I'd say just a positive 3, because we were taking an odd root of a positive thing. We get a positive real root. Cheers.